In this video, I'm going to present some mathematical preliminaries, really just to remind you of some of the background information that you would have learned previously in your math classes, but also to bring everybody up to the same speed. Since this class has no prerequisites, there are people who have very different mathematical backgrounds, and I want to place a consistent foundation for everybody in the class. Another aspect of this is that the notation that we use statistically is a little bit different than the notation that you're probably accustomed to in mathematics. So it's important that I communicate the basics so that you can see the notation that we'll be using throughout. Lines are usually given an explicit description of the form y equals mx plus b. Of course, that's a function of x, so we write it as f of x. Here, of course, m is the slope and b is the y-intercept. The y-intercept, remember, that's the value of y when x is equal to 0. I'll come back to that in a little bit. In statistics, we almost always write this like this. We'll write this as y equals f of x. Again, you're seeing that given there again. Given beta naught, beta 1, or sometimes we'll lump the beta naught and beta 1 together as just this kind of bold-faced beta. And you have beta naught plus beta 1x, okay? There's no difference between the two descriptions of the lines. Beta 1 obviously is going to play the role of m, and beta naught is going to play the role of b here. And of course, we change the order of them, which is kind of customary in statistics. So again, beta 1 is the slope and beta naught is the so-called intercept. Now, every pair, beta naught, beta 1, corresponds to a distinct line. And in that way, you can kind of think about the pair beta naught, beta 1 as kind of like the name of the line, maybe like a first name, last name. Every different line gets a different pair of numbers, or every different pair of numbers gives you a different line. This equivalence between lines and points actually has a really nice illustration that's associated with it in terms of two Cartesian coordinate systems. So here's the beta naught, beta 1 plane, and here's the xy plane, okay? The idea is that points in the beta naught, beta 1 plane are going to correspond to lines in the xy plane, okay? For example, here's a point on the beta naught, beta 1 plane. Its beta 1 value is 0 because it's lying on the so-called x-axis, the beta naught axis, which means that it has no slope associated with it. But it does have a beta naught value that's positive. So this is going to correspond to a line in the xy plane that's flat and has a positive y-intercept. How about some others? What do you think this line is going to look like? Well, beta naught is 0, so that means that this line is going to have to go through the origin, the point 0, 0, and its beta 1 term is positive, the slope is positive, which means that it's going to increase something like this, okay? And we could do this with different points and so on. Every different point gives us a different line. So there's a correspondence between points in the beta plane and lines in the xy plane. We'll conclude with three simple properties of lines. First, the slope is the rise over run, and the interpretation of the slope is that it is the change in y per unit change in x. The way that we can see this is that if I look at f of x plus 1, and f of x is that beta naught plus beta 1x, this is equal to this just by substitution. I can then push the beta 1 inside so that I get this. I'll re-aggregate beta naught plus beta 1x, and I'll recognize that as being f of x plus beta 1. So I've changed x by 1 unit, I've added 1 to x, and that has effectuated a beta 1 change in y. Second, a change in y per unit change in x is the same for any x. What do I mean by that? I mean that the interpretation of the slope of the line holds for any x, okay? This interpretation is said to hold globally, meaning regardless of what x is, the interpretation of beta 1 is the same. Importantly, this is only true of lines. 3. 2 points x1, y1, and x2, y2, meaning those are two different points in the xy plane, those are going to uniquely determine a line. And that line is simply the line that goes through both of them. Points that all fall on the same line are said to be collinear with one another. In the practice, of course, it's very, very rare to see points that are exactly collinear. So that's all we need to know about lines. Let's move on to the next lecture.